Hey, welcome. So today I'm just going to show you some of the new features that we've built into CFMA. So we've built in support for metric and imperial units now with conversions implemented into that, and then some support for direct strength method for design functions post-analysis. So we'll just start off with a simple section. Now we've got a default one loaded here with some properties calculated when you load the app, but you can use the template selector from the section builder here, select any type of section, and then enter the properties to drive the geometry. Once you're ready, you can click on Use Template. That'll then add it to your list of sections here, and you can choose which one you want to design for. You can also use the Drawn tool here to create a new profile. So if I click here on Clear and Draw and start selecting points to create my new profile, it'll then simply start creating that geometry. And of course, once we're done, all I can do is click on Stop Drawing, and we can then head down here and say Use Drawn section. And you'll see when we add that, it'll compute the properties automatically. I'll just remove this one again since we're going to use our standard cold formed lip channel default section here for this example. Now, if we head over to analysis, you can see that by default we'll run a elastic buckling analysis. There's some other options. We'll just stick with elastic buckling for now in order to run the direct strength method downstream. The solution is going to be signature curve, and then we'll just keep it as a pin-to-pin support. So the entry elements here follows the same logic as with CUFSM in MATLAB. You can specify the member length. If you change the values here, the only important thing is we'll do the loads in a second, but the only important thing here is you can click on auto sweep, and that will then create the half wavelength sweeps for you automatically based on the length that you entered. When it gets to stress generators, or the loading that we add to it, we can either use reference applied loads, or we can use the first yield calculator. And whatever button we click on here for the various principal or geometric unrestrained values will just be copied or processed across into these values here for forces and moments. I'll just enter mine manually. So we'll do a 5 kilonewton actual force, and we'll specify here, let's say 10 kilonewton centimeters for that moment. And when we click on Submit Stress to Section, you'll see that that will generate the stress diagram for us. Okay, so now that we've got that entered, we can go ahead and run the analysis. So what I'm going to do from here is I can either choose Analyze from the top, or we can go run analysis here from the bottom. But before I do that, let me just talk about material properties. So if you wanted to adjust material properties, just go here to the tables workspace and click on the prop 1, and you'll see in here we've got an ID, and then we've got modulus of elasticity and other properties that you can enter here for your materials, and that's what would be used for this section. Okay. Now that we've got everything in here, again, maybe if I head back to tables, you'll see here, this is a breakdown of the elements. So here is the nodes that define the cross section. Here is the elements for the finite strip, and you can see there that we've got those material IDs mapped there, 111. And if we look at the property here, it's 111, which means if we add a row here and we gave it a different ID, all we need to do is make sure that it ties up here. Now that we've got that done, let's run the analysis. This might take a couple of seconds. It doesn't take too long. So we'll just let that run through, and then we'll look at the results that we get out of the buckling analysis here. By default, it runs 20 buckling modes. So just before we go to the results, at the bottom here of analysis, you'll see it's got eigenvalues there, and the number is 20. That's the default. You can increase that or reduce it as you see fit. But once it's run through, we can see that it defaults to the maximum half wave length and shows us the mode 1 shape there at the moment. We can drag the slider across and see the different stations along the length of the element with its output here in the screen. And of course, if we change the mode here or use the left and right arrows, that will then jump between the modes. We can do the same here in a 3D view. So that's currently showing us mode 2, now mode 1. the half wave at that length, and we can adjust the length slider here to see the various outputs. Or we can click on full member, which will just show us the full member length in 3D all the time. And we can click on the play button there to simulate that. If I click on reset and change this back to half wave and switch this back to, let's say, 140 millimeters and play that again, we can see what that looks like, and we can repeat this process for all modes. We can also do this in the 2D viewer. So if I click on play here, you'll see that that will just add to the exaggeration scale on that deflected shape. All right. And you can, of course, manually adjust that deflection scale here as well if you wish to. Now at this stage, we've got some outputs here, so you can see it's giving us a load factor that is at this specific half wave length. So if we change the half wave length value, you can see the load factor updating there. We can see at the bottom here, we've got the buckling curve, and if we select on any of these locations here or data points, it'll then jump to the relative half wave length that is associated with that. We can also click on the dock button here to fill the screen, and we've got this YMax slider that just helps us normalize this into the current view so that it presents a bit better at full scale. We can not always see as clearly since our first mode there at the beginning where the length is 2 millimeters. You can see that in the display here at the bottom when I hover over the node is quite short. So if I reduce that, it just means that we can see a normalized view in the screen. Undock places it back in its location here in the results panel. Now, we can go ahead and do a direct strength method design routine. So from the design basis dropdown, I can choose core principles for nominal checks, or I can choose code-based design checks. So currently it supports the Australian New Zealand standards 4600 of 2018. There's also the American standard S100 of 2024. We'll use the AS-NZS one just for this exercise. And what I'll do is I'll click on Run Design. This might take a little bit longer. It's got a lot more work to do. So we'll just speed up this process a little bit, and I'll show you what it looks like once it's done in about a minute and a half's time. Okay, so we can see that it's now run through all of those checks. And from here we can see still on the results panel, the DSM design, the direct strength method design panel is now expanded. We can see a bit of information here, the standard checks that has been applied, and we can see some outputs here. So what assumptions has been made, initial values, and then some checks that have been performed. So we can see here exceeds nominal limit for the beam column interaction. We can see tension plus bending interaction is okay. We can see here the moment and shear interaction within nominal limit, and so on and so on. And then down here is a summary that just shows us those checks that have been performed against the relevant standard. And these bars here indicate demand, the nominal capacity, and the design calculated values. And then down here is a table again with some tabulated output. If we click on the dock button, that just docks it in the screen and gives us a bit of a better visual in terms of what's happening here. And undock again places it back into the results panel. There's a couple of warnings and limitations depending on the standard that's selected, so I recommend that you read through those and understand what those are. And there's also an audit trail that gives us a bit of background in terms of what modes and section values and properties or result properties were selected for the DSM run. Now from here, the next step would be to start producing some report output contents. But before I do that, I'll just change the title here to Demo CFMA Project. Oops, there's a typo there. Let me fix that. All right. Now, the reason I did that, and you can do it later on as well, is when we generate the design pad report, it's going to place that in the title there for us. Of course, if I change anything here, it will just add it onto the report. So it is dynamic, and you can update that at any point. The report by default's got everything selected. Since we have a DSM result, it'll include that. If it wasn't available and you just ran the buckling analysis, that will just be unchecked and unavailable. But if we scroll through here, we can see we've got graphical outputs and tabled outputs with a whole lot of information. The actual results on buckling curves is quite lengthy. So what I'm going to do is I'm going to uncheck that just to reduce the size of this report. And you can see now we get to the DSM nominal design summary. We've got our second order basis summary, assumptions and scope, the audit trail, the nominal checks, against the standards and where they are relevant. We've got the interaction checks, we've got bending shear interaction, we've got tension bending interaction, buckling analysis results, and then formula used for the outputs. And then that's followed by the buckling curves for the different modes at different for the project. Then we've got our DSM summary snapshot there. We've got the stress diagram snapshot, and then we've got the different modes and stations outputs 3D followed by 2D cross-sectional views, and that makes up the entirety of our report. And once you're happy with the contents of the report, you can export that to Microsoft Word format. So when we click on the button, it'll prepare that and produce the docx file that we can open up straight into Microsoft Word and continue downstream editing. Nicely formatted, nicely presented, similar to what the design pad output looks like. So there you go. Formulas are real equations in Word, so those are all transferred as you would expect them to be. And there you go. That is how you use CFMA from start to finish. Feel free to play around with the software. It's free to use. However, to run the analysis, you would be required to log in. So if you haven't got an account yet, register one. It's easy. Provide an email. It has to be a business email. No Gmail, Hotmail, Outlook, Yahoo, and so on. Specify your name and surname, your company name, country, set up a password, and register. You can then choose verify email to send a verification code to your email, which you will then enter in here to finalize your registration. Please check your spam folder. Sometimes they get stuck in there. If you don't receive a verification code for whatever reason, you can click on manual activation, and that will send an email to us to manually activate for you, which we can do if you require it. Hope you found that useful. Hope you like the software, and happy designing. Have a good day. Cheers. Bye.